Welcome, everybody. Are we ready to rock and roll? All right. It is so much fun to see a room that is filled up to listen to physics. I mean, you know, this is like, you know, let's break every stereotype out there and show what this university is all about. It's wonderful to be here with you all, and I want to give a special welcome to Regent Rogelio Riojas. Thank you for your longtime leadership of the Board of Regents, and I know that there are other regents that are watching online, so thank you very much for being here, Rogelio. And this is really one of my favorite events, but I want to begin with UW's land acknowledgement. The University of Washington acknowledges the Coast Salish peoples of this land, the land which touches the shared waters of all tribes and bands within the Suquamish, Tulalip, and Muckleshoot nations. We're all here for one reason, and that's to listen to this year's faculty lecture. This is the highest honor that we give to a faculty member at the University of Washington, and it is given to them by their peers. It's not given to them by me, as much as I know that's important, but it comes, and so it really is a big deal. And we're very lucky to have the Arthur B. McDonald Distinguished Professor of Physics, David W. Herzog. He's director of the UW Center for Experimental Nuclear Physics and Astrophysics, and he currently leads the Precision Muon Physics Group. Now, I know that there's probably maybe at least 2 or 3 people out there, including me, what's a muon? Well, you'll know exactly what it means by the end of today, no question about it. Professor Herzog is exploring some of the most fascinating and provocative questions about how our universe works. In some ways, you know, what's so much fun about physics is that it's those questions that you have as a child. How do things work? But now you really can see how all those questions do in fact have answers, and we are exploring them. And his group's cutting-edge experiments with subatomic particles are revealing clues to some of the most persistent mysteries of particle physics. His work lives at the boundaries of what we understand about the fundamental laws of physics, but it pushes those boundaries into truly uncharted territory. As a teacher, mentor, and collaborator, he's leading some of the most exciting discoveries in the world of experimental physics. This is going to be fun. His curiosity-driven research embodies our university's mission to pursue discovery that expands humanity's knowledge and understanding of the world. Professor Herzog has received numerous awards and recognitions for his groundbreaking research. They include the Tom W. Bonner Prize in Nuclear Physics, the John Simon Guggenheim Memorial Foundation Fellowship, and the American Physical Society Fellowship. And he was the 2022 winner of the UW University Faculty Lecture Award, which means that not only can he do mind-blowing research, but he can explain it in a way that even people like me might be able to understand, which is why I'm so excited to be here. And he's a founding co-spokesperson of the muon G2 experiment at the U.S. Department of Energy's Fermi National Accelerator Laboratory. I know that the reason why this room is full is we're excited. We want to expand our horizons as well. And today we're going to learn about unpacking the mysteries of the universe. So it's with a very warm welcome to Professor David Herzog, the University Faculty Lecturer.
Okay. So first and foremost, I want to thank you for the honor of inviting me to this, to speak in front of the university community today. It's extremely rare for someone in my field to get a platform like this. And I would like to be able to at least express the passion for which people like myself do this work day and night for years and years on end, sometimes after a very long time, simply to reveal one number, which you'll see. And today, I'm going to tell you a story. I had the honor of knowing about this lecture 8-9 months ago. So as I like to tease my others, I've written 3 really great different lectures you won't get tonight over the years. And today, I'm going to tell you, I thought in the end of the day, I really want to tell you a version of this story, the real story that probably got you to invite me in the first place. And the interesting thing to connect, since this is a university-wide talk and not a talk just to a physics department, which I'm more used to giving, I thought I want to think about it a little bit differently than the way I might give a technical talk just to other experts. And I thought, well, in our field, the interesting thing about physics is we're not typically organized around what you might call history. We don't learn necessarily the history of each science thing. We basically tend to teach our students what's here and now and known and go forward from here. So I was looking back and trying to prepare this lecture, and I tumbled into some beautiful history that I didn't know associated with my story. So in the honor of being able to give this lecture, I too learned a lot, which I hope to share a little bit of for you today. So what's this all about? Well, in April of 2021, this story that I'm going to tell you made the front pages of newspaper articles really all over the world. Fermilab tabulated several billion eyeballs that had seen this information. And if you didn't want to read it in one of these different languages or so, you could also read it in one of the cartoons, because in fact, this PhD comics cartoon absolutely brilliantly gets it. I have to say, probably better than most of us could give the talk. And what was the buzz about? So the buzz was about, and keep it this way, you only need to look at some of these plots to see where the dots are and where they aren't, right? So in this particular case, there's a measurement here, and what does it say? Basically, there's a theory for what this number should be. Who cares what the number is right now? There's a theory by very bright people for decades what this number should be, and then there's the experiments. And the experiment that we finished in 2004, which I was part of, had this number, and this was pretty far away, and the one we just measured after all this time matched it, put them together, and you have this thing called 4.2 standard deviations, which we quickly calculated today with my good friend Jason here. It means 99.997% chance that it's not a statistical fluke. But in physics, that is not good enough. That is not good enough. So what was measured, here's 3 things to get us oriented. What was measured, how was it tested, what was it being tested, and how well was it done? And then I'll double back. So 3 quick answers before I get to the beginning of this talk. One is we measured something called the gyromagnetic ratio. So you can remember that word if you want, or you could just remember this letter G. G is what it is. That's enough for the G2 and so on and so forth. And what is it testing? It's testing whether the standard model of particle physics is complete. Do we know all the bits and pieces of the way it is? And this is a thing that sort of probes it in some way. So the theorists, they predict this number. The reason we can do this is they can predict this number to extraordinary accuracy. But we, experimentalists, can measure it to extraordinary accuracy as well. So you match those. They predicted a number, we got a different number. That's what I was showing you on that graph before. So just to give you an idea, I'll use sometimes the word parts per billion, because that's the world we live in terms of precision. And we're eventually measuring something to 140 part per billion in precision. So I'll tell you a bit more what that means. Now let me tell you the name. It's called the G-2 experiment. It's not the G experiment, the G-2 experiment. And it's because of this funky thing. We actually determined this number. That's enough digits that it makes a very good password for half the collaboration. So you could probably break into a lot of bank accounts if you can write that down. So the difference of, on the other hand, this little number here, if you take this big number and subtract 2 from it, you get all this stuff over here. The experiment is cleverly designed to just measure this stuff over here. And that's why it's called the G-2 experiment. It's the difference of 2. We can do subtraction. So what is 140 parts per billion? So it turns out that this is a nice example. Here's a puzzle of the first page. You can buy this at the Fermilab gift store. I do not get any proceeds from that. And colleague, Steve Sharp, bought this puzzle and built this puzzle. The sad thing about Steve Sharp's version of this puzzle is somehow he was missing 3 pieces. That's three parts in 1,000, and he wasn't getting that right. And I thought, well, this is an interesting thing to give us an idea. So, for example, if I took the puzzle and I shrunk it down and I multiplied it by 1,000, 132,000 piece puzzles, if you had 132 of these and you built every one perfectly except one piece was missing only, that's already 7,000 parts per billion. So you'd actually need to have 7,000 of these puzzles. It takes a long time to do that, and build every single one, missing one piece to a dog that got it when you weren't looking, and that's 140 parts per billion. So it's not too intuitive to be down in this level of numbers, but that's where we are. So let me start in this place that I didn't know so well called the past, back to around 1900 or so. And tell you, it's interesting, we never learn when did they learn this stuff, but they did know about magnets, magnetism, electricity, and stuff like that already in the 1800s. So let me think about magnets is this. Basically, a magnetic field is produced whenever there's electric charge in motion. So like the strength of this thing is called the magnetic moment. And you know, kids do this. How many people have done this kind of nail thing with their, you know, and then we certainly know in industry we could pick up stuff like that. In medical industries we have magnets like that all the time. And this was actually pretty well known by the early 1900s. But what wasn't known is what's happening in that. That's the bar magnet, right? What's happening in a bar magnet, because it doesn't look like I see any electrical currents connected to that bar magnet in this picture. In fact, although there is a magnetic field that you could trace around, and we do that often in the introductory laboratories at the university classes, right? So of all things, so when Richardson in 1908, it's a guy I don't know, in 1908, I didn't know him, well, and he suggested a really beautiful test. And I'm sorry, but there will be an equation coming up in the next 30 seconds, so hang in there. It's not a difficult one, but it's important to understand the idea of G, or the gyromagnetic ratio. And it basically goes like this. He said, look, here's just a circle. This is nothing special, and there's an electron there. This electron is here, and it's going to has this circle in a moment here. So as it zooms around here, like that, making that sound as it goes, it's creating an electric current. You could think of an electric current just by one electron going around, and it has a few properties there. I have the velocity and so on. It doesn't matter so much. So let me go around one more time and remind you of the things that go around one more time, like a skater, like a dancing skater that goes around like that, spins around at the end of her routine. And that property is called angular momentum. There's an angular momentum. So now you look at these two things, the two equations are there. You see some E's and V's and M's and so on. And if you divide those two, the velocity disappears, the radius disappears, and you get a constant. The constant is the electric charge divided by the mass in a factor of 2, and they knew that stuff. They knew that stuff way back then, and so it was a remarkable thing. Now, if you put a little g there, remember the g from the beginning of the talk, and g minus 2, and so you stick a g there, well, the value of the g there would just be 1, because that's remarkable. And so that's a sort of a classical magnetic moment, okay? We have that gyromagnetic ratio. And that's what they thought had to be the case. So the idea of this was, of what to do to test this, was tested by, of all people, Albert Einstein. We think of Albert Einstein entirely as a theorist who did lots of, let's just say, extremely important work. And hardly any time, I've asked in an audience this big, almost of physicists, how many people knew Einstein did experiments? And one hand would go up, maybe 2. I didn't know that at all. Most of my colleagues didn't know that at all. But he spent years of his life because he totally thought he's got to chase this down. And now you'll see a little recipe of what he's going to try to do. He wants to find out what is going on inside this piece of metal that's not connected to electrical wires to make it a magnet. So the idea, the recipe, and this is a Wikipedia version of the thing, but the paper is quite beautiful actually, is you hang on a fiber a piece of metal like this, ferromagnetic metal, and then you have some coil around it like that, and you wrap it. And then what happens is, if you turn on the magnetic field of this little piece of metal that's just dangling there like that, and all of a sudden you line up its magnetic moments like that. Well, in order to preserve angular momentum in this ratio, the thing is going to turn. So that's what they tried to measure in a fancy way. And it goes like this, okay. And by the way, they said, okay, assuming the magnetism of iron is due solely to the motion of negative electrons, the torsion reaction should easily, that's the reason I put this in, easily give a talk. And I shout out to a book down there that I absolutely think you should read. So here's it is. Notice I just flipped a switch over there. It's in blue at the bottom. A blue switch there with the power supply is going to make a current go like that. The current goes around like that. It makes a magnetic field like that. So they throw the switch on and off, and then they have a mirror at the top, and the mirror at the top shows the very, very slight deflection of this rotation. They did it very carefully, and Einstein, he's a heavy name to drop, right? If Einstein thinks this has to be the case, these molecular currents, the community thinks this has to be the case. So they expected to get G equals to 1, and in fact, he got G equals 1. And he got it to 10%. It was a beautiful thing, and he was happy, and people ran around, and so on. This was around 1915. You can see at the bottom, I have plotted his result, 1. Now, it was wrong by a factor of 2. It's completely and utterly wrong. It's not at all what's happening inside that metal. But, you know, it took like over in Princeton, a grad student on the other side, no internet, no talking, to sort of start getting numbers like 2 in the early experiments, which you begin to see here. And of course, all of those people were writing things like, I'm really sorry I got 2, maybe I had something wrong, maybe there was positive charge going the other way, and things like that. But in fact, it is right. And it was not until later, like in the mid-20s and onward, in which we really learned the theory through Dirac of relativistic quantum mechanics and the quantum nature of a quantum particle like an electron, in which we know the spin is in fact a intrinsic spin of a particle and is a G factor of 2. And that is the right answer. And the muon is just like an electron because they're brothers, and so it is also 2. So that's the 2 and the G minus 2. Okay. So let me fast forward to the next sort of era of interesting discovery. And I can't tell these stories as long. So if I'm ever going to get to my story, I'll have to make these 3 brief. But basically, in the mid-30s or so, people started to have electronic detectors and different kinds of detectors, and they were looking at cosmic rays. And they started to see very strange things in cosmic rays. And over a period of 18 years or so, they started to find these unexplainable penetrations of very, very energetic particles that blasted through the ceiling, blasted through detector here, a big chunk of lead there, another detector on the floor, and that just wasn't what an electron or any other known particle would ever do. So they had quantum field theory at the time, a very early version, and they were absolutely they were just about ready to kick it out. It was failing to explain fundamental what they call radiative processes. In fact, it was Oppenheimer who basically said, hey, it's either gone or we have to have a heavy new kind of a particle there. And so, in fact, that heavy particle eventually, it's the muon. The muon is penetrating through all of this stuff, and we're getting rained on by muons right now. They're going through you. You can count a few as you go here, 1 per centimeter per squared per second, a number we use in the lab all the time to test our detectors. The next thing that happened a bit later, now we jumped another decade, is people started to do really beautiful atomic physics experiments, things that I could tell you more about, but I'll just keep it light. And they started to now get the precision on this G factor, not just at 2, but you could see the number there already, 2.002. There was a Nobel Prize for this kind of work. And I, again, love these sort of remarks in papers that show up that says, you know, aesthetic objections could be raised against such a view. You know, but we'll come back to that in a minute. And then another one, and again another decade later, and this is a picture of Madame Wu, and you see it mirror reversed. Madame Wu's picture mirror reversed. The concept that space is not symmetric left and right in a certain kind of reactions. They're called parity violation. Parity violation for that came upon. And this is beautiful enough that we need one more slide on that, because it was really the work of Li and Yang, a really radical thing in which a Nobel Prize was won exactly about a year later. This was one of the only times things happened fast. But in fact, the suggestion of whether in the weak interactions have things like radioactive decay and muon decay and things like that. That the parity is not conserved was in this paper. And in this paper, they had recipes for all kinds of experiments you could do. One of them was picked up by their Columbia colleague named Madame Wu, and she ran off and did that. Another by these gentlemen here, Garwin, Letterman, and Weinrich, who ran off and fiddled with their experiments. So you see the dates of these papers are close. Now, the reason Li and Yang thought that was, again, there was data that was just driving everybody crazy that made no sense. I won't go into that, but there was a long period of what the heck is this stuff? And so in this paper in 1957, they basically showed that what Li and Yang said is, hey, if this is the case, that particles are left and right-handed and such, then a pion would decay to a muon, and the muon would be spinning like a football. If you think about a spiraling football, it would be like that. And not only that, as the muon is spinning like that, when it decays, it would spin throw its electron this way or that way, again, related to how it was spinning. And that recipe led them to say, this is a little magnet. And if it's a little magnet, I can put it in a big magnet and get it to, sorry, I should get it with this, you can get it to kind of oscillate like that. And that was dead proof that this was right. So again, back to the muon, we used the word magnet. We used that kind of word before. And basically, if you think of our little muon, it's a tiny little thing, as a little bar magnet, it will be very helpful now as I go to the next step. So the little magnet sits there, and if you put that magnet inside another magnet, it's going to wobble. It's going to wobble, and sometimes we use the word precess, but just like a toy top, the very picture that you see right here is what's happening. So that's the nature of these experiments. You stick a little muon in, and it wobbles around, and you figure out how fast it's going to wobble around like that. That's what gives you the number. Yeah, but remember I said that G is the 2.002 is not 2, it's some other slightly number. So you're going to say to yourself, okay, Dave, why is it not 2? It looks like a little thing like that. So what is the answer to that? We got the wobbly thing going there, and we got the spin and the direction and the magnetic field going there. But what we didn't have so far is all of the quantum fluctuations that the muon is sensing. It's sensing the whole vacuum world that it's around. It's sensing absolutely all of the particles that exist in the standard model, which perturb it ever so slightly and cause it to wiggle around a little faster than it would if they weren't there at all. So it is a probe of everything, okay? And if we have all the everythings accounted for, we'll know how fast it ought to wobble. Now I get a chance to tell you about something I thought, no way in an audience, a general audience, am I going to try to do this? I said, yes, I am going to try to do this. This is now at the level of Richard Feynman's, what I'm going to call hieroglyphics. So what is a hieroglyphic? I thought, well, believe me, the scholars in here will tell me I got this wrong. But to me, a hieroglyphic here is an image like this in which a learned person trained in the art can take this image here and actually turn it into in this case, a mathematical calculation. And anytime I draw a version of this, you can do a mathematical calculation based on this. And what does it mean? Well, in this world here, you have a muon. He's sliding along in time here, feels a tickle of a magnetic field, and does one of these fluctuations right here in the quantum world. This is the simplest diagram. And without this diagram in front of him, Julian Schwinger actually calculated this. These are Nobel Prize winning things for the beginning of what's called quantum electrodynamics. And Julian Schwinger was really proud of getting the number alpha divided by 2 pi because he stuck it on his gravestone right here. And that's where some people say he was a good father, he was whatever, and they put alpha over 2 pi. It's an important thing to do. There are now 12,652 of these crazy diagrams, all complicated, twisted things calculated. And the man who led this is Tom Kinoshita at Cornell, who I just learned died 5 days ago at 98 years old. He spent his entire career developing the mathematics of this. It's the most extraordinary, most precise theory in all of physics. Okay, so you too could draw diagrams like this. And I did this actually at a kid's, this was weird. I went to a kid's museum and I used the light board and I made Feynman diagrams, and then people looked at them and just changed them. But you can make these little things with your muons and stick in other particles that you know. You look up the particles in the standard model, you can draw these things, and you can see they all kind of have the same thing. Then there's one here this one I might mention at the end. So if you want to pay attention to this picture now with the blue blob in it, the blue blob is important in that way. It'll come later. And then if you can come up with anything, this is the kitchen sink. So you can stick anything you think might be in there, and in principle, you could calculate the effect on G minus 2. So that's why the logo of our experiment looks like this. It has a blob that says G minus 2, because that's what we're looking at. We're looking to see if there's anything that we don't yet know by one of these. So this started a 60-year campaign now of people trying to measure G minus 2 of the muon to higher and higher and higher precision. Always with a cat and mouse between the theorists as they calculated more of the diagrams, and the experimenters did a better job, and back and forth this went on the development of physics. So in this particular early case, you see, I don't even know what the number is, 4,300,000 parts per billion. Then they decided to put it in a ring, and that was a little bit better. And so you can see the wiggles get a little bit better here, and they're already doing a good job at 265,000 parts per billion. And then they decided to put in a bigger ring, and this bigger ring had a breakthrough idea, which too tricky to talk about at the moment in a minute, but it was a good idea, and that led them to 7,000 parts per billion. And then we did a new experiment at Brookhaven National Lab in New York way back. This is how I got introduced about 30 years ago to this, and an experiment led by Vernon Hughes. And if you've got a really sharp eye, you'll see a very young Dave Herzog sitting here. All of us are standing on top of a superconducting magnet. The Department of Energy would never allow this photo now, but there we were sitting on it at the time. And the idea then was that made a big breakthrough as we figured out how to absolutely directly inject muons into this ring so they could go around. And that, prior to that, was not trivial. And so we ended up with this result I showed you at the beginning, about here from about the year 2004 when we were finally done with the measuring program. And over the years, this was the theory, keep improving, keep improving. And here in Seattle, actually, there was a really big conference with all of the theorists who calculate this stuff, and we ended up with this number right here in red, and you can see the red number differs again, which we started this talk with from the measurement program right here. So maybe the measurement's wrong. I mean, it's the only one that's there. After all, nobody else measured it, and there's a whole lot of other people measuring theory, so we got outvoted by that. So, or it could look like a very interesting crack in the standard model particle physics. Maybe there's something missing that the theorists didn't calculate. That's the idea, that they calculate everything they know, but if there's a new particle out there, if there's a new kind of interaction, they don't have that in their theory, and that would cause the gap, that would cause the muon to wobble faster than it normally would. So we developed a new experiment. This is the experiment I co-founded. Again, I was on the other one, but then I just didn't think it made sense to let that rest as a kind of a, somewhere in the unknowns of physics, not resolved. And so just to give you a sort of flavor of the kind of experiment, here we are in a planning meeting right here. I think you can recognize the fountain. But there's 200 of us from 35 institutions, 7 countries. It's about $100 million. It's now 13 years going strong, and all we get out of this is one number. Well, I'm sorry for those people who have to look at my, productivity paper list. It's not as high as it could be. But and in any case, the interesting thing is, this kind of takes a village comment. The experiment involves physicists who are in particle physics, nuclear physics, atomic physics, optical physics, accelerator physics, and theorists. It's a community in which we rely on each other's expertise. Not one of us is competent enough to go through all of this, and it makes it such a learning opportunity for each of us as we learn what you do and why you know this and so on. That's why I've enjoyed it so much. It continues to give interesting clues away. Of course, the reason to come to the University of Washington, the invite was, this is an extraordinary place to do precision physics. The laboratory SEMPA is the place in the country you would want to be. And over the years here, I was fortunate enough with my colleague Peter Camel here. Peter and I are, brothers in all of this for a long time now. All of our students, our postdocs, other faculty, research scientists, and so on that have been part of this project along the way and are still part of it and are still, as we speak, we are taking data right now, and one of our postdocs is running it. One of my students is on shift. I mean, that's the fun thing about this. It goes on. So let me remind you, now I'm going to turn to how this experiment works in a few minutes here. Let me remind you that what we've been looking at, right, is always some kind of a muon that goes inside some kind of a magnet and wobbles around, right? That's the idea. So to do that, you have to measure how fast it wobbles around, but with just as much precision, absolutely equally or better, you have to measure what was the magnetic field, because they go into the equation as a long division. And then you just use the following mathematical technique we all remember from 4th grade called long division. We just divide one number by the other. It's not always that easy. So I thought I'd put this little, it's funny with the GIF, but I thought this would give you, again, a reminder. If I spiral a football, again, it has angular momentum, it has a spin, it has a direction, and as it goes into the magnet, it's going to go around and around in a circle in the magnet. And if you think about a punter kicking a football where it starts to go end over end, this thing is going to start to go end over end. And every 29 times this football, called a muon, goes around this ring, its spin goes around one extra time. That's what we measure, that extra time. Yeah. Okay, so we needed a magnet. So we thought the magnet that we had in New York was such a special magnet, superconducting magnet, fancy deal. So we wanted to have it, so we took it. So we, well, they let us take it. But a superconducting magnet has these coils that you cannot flex by more than a few millimeters, and now you have, and they're 50 meters or 50 feet or so. Out the door it goes, onto a special truck, onto a barge, all the way around the waterway you see there, you see it going by St. Louis. Then we get it within 50 miles of Fermilab. We had to close the highways 3 straight nights with a 30-car caravan, go through the toll booth, pay the toll, and have it arrive at Fermilab, and then you have to put it back together. And I was in front of a committee trying to argue for the case of this one time with my peers outside it because I was leading. I said, and then we just put Humpty Dumpty back together again. And I thought that was cute. And then I came out of the meeting, and my colleagues are around me. They surround me. Dave, don't you remember all the king's horses and all the king's men can't put Humpty Dumpty back? Oh, no. But we did. And over the course of a year, we put all of this together in terms of a magnet. And UW people did a lot of work in this thing, as you'll see some in some of the scattered pictures here. And this is a picture from SEMFO where we created 8,000 tiny little strips of iron that went into the thing just nicely like that. And some of our people putting them together to make it work. But that's just putting the magnet together. Then you turn it on with the power, and it's a lousy magnet. It's really lumpy, and it's not too smooth, and you want a really good magnet. And so you proceed to do something to smooth it out, which is why this made it good. It's called shimming, like you do. And the interesting thing I thought I'd tell you is the connection here is it's the same techniques that does your MRI. When you get an MRI magnet, this is magnetic resonance imaging. We call it nuclear magnetic resonance. You're not allowed to use the nuclear word, so we said magnetic resonance imaging. And we built on this little bus that you see right here is a trolley. And the little trolley here has all these little probes in it, and we drive it around inside the ring. And everywhere inside the ring, you see it measuring the quality of the field there. As it's measuring the quality of the field, we're doing this, and then we come back, use some mathematics, and smooth it out until in the end of the day, this is a picture of the average magnetic field all the way around, and it's at the part per million level. It's like very smooth. It's a very, very smooth operation at that point. A big deal. UW did a lot of that. We built all these probes and such here. And then you need muons. Where are you going to get these darn muons? So the reason is we went to Fermilab. This was Peter's idea. Peter Campbell said, we should do this experiment at Fermilab where we can get these muons. So I said, oh, Peter, we're going to have to move the magnet. He said, you should do it. So we did that, and then here's how you get them. You start off at Fermilab. It's a top-down picture of a pretty big thing. I hope you can see the sizes of the buildings and so on. The protons go around and around. We break them into 4 batches there. One by one, they smack into a target down here in the bottom, which you see here. This is now 300 meters. There's pions here. The pions decay to muons. They go into this triangular thing, and they get dizzy running around there. And all the background particles go away while they get dizzy running around there, and then we inject them right into the muon ring. This is 2,000, this is a long way. They go a couple of kilometers to get to us through about 1,000 magnets that all have to be tuned just right. And that's just to get the muons to us. When they get there, we have to bring them into a back door in this superconducting magnet. There's a very clever little hole in the back door and a fancy magnet. And they come in like that football. And the football is, okay, the football, this is the spin of the football in red. And what they do is they go around in yellow like this. But as they go around, bit by bit, this football starts to go a little faster. It's like ahead of its class. So it's turning around faster. And that's the thing that we measure. And the reason we call the measurement G-2 is measuring that frequency is proportional to G-2. It's not proportional to G, so we really gain a lot. So this is some stuff I built basically to measure that wobble frequency. The muons decay, and this is the ugliest picture I could come up with, along with an ugly photograph before it got nice. But the muon decays, and it goes in and hits one of my detectors and makes a flash of light. An electron makes a flash of light. And the flash of light is proportional to the energy. And so here's a sequence that you'll see. The wobble rate is visible if you record just the really big flashes and not the little flashes. So there's detectors all the way around the ring. They all look like this. They all stick their nose into the magnet. They all are made out of these 1,300 pieces of incredible glass. The electron hits it, makes a big pulse, and this little animation showed you the arrow. If the muon is spinning in the direction it's going, like now, it makes big ones and little ones, and big ones and little ones. So we use that big ones and little ones as it's going around and around and around. We start the clock, and this is what we get. This is real data coming in about 6 minutes. It just builds that wiggle plot up. It's like trivial. I mean, the people that did this 60 years ago would be struggling with this. Okay, so in the end of the day, we do this for years and years and years. And we collect a lot of this stuff, this wiggly data. And there's millions, just billions of these electrons are in there. And in practice, anybody in the audience can see, I hope that you realize this is just wrapped around. Otherwise, this plot would go off to the next campus. But basically, it's pretty easy to see there's one frequency in there. There's actually a few others, but we fit them out. Now, the key about doing this in the modern era, and every experiment I've been doing for the last 20 or 30 years, is we do them, this is the remarkable thing, we do them blind. We do all of this work, we analyze the data for many years, and we have no idea what we're getting. And the reason that we do that is basically, and how we do that is I told you we do frequencies. So every time you do a frequency in an experiment, you have some kind of a clock. Something is ticking at 1 second, 2 seconds, and so on. So we have people come in and change how fast our clock spins. And then we just measure everything in terms of whatever those seconds were until eventually we figured out. Now you see over there the blind tasting. I've got somebody drinking wine over there from my good friend Jay Shearing, who is a wine expert. Now the difference between a blind tasting for wine is if they actually have tasted that wine, they can tell you what it is blind. But we have no analog to that. We have no way to get out of this secret box until the end. So we have these two people in management, usually a president of the university and the provost come along, and they take the clock and they spin it at some level. We give them guidance so they don't do something crazy. And then they write it down. It's in locked panels like that, and they put these things in secret envelopes, like this one here. This is one of the envelopes, and it's ripped, so I've sneaked in. Then, of course, this was unfortunately during COVID, so we did all of this analysis mostly from our bedrooms for over a year, and everyone's on screen that could be, and you have to take a vote, and it has to be a unanimous vote, and everyone has to agree that this is what you do. And when you do that, then I take my envelope and I pull the secret numbers out of here, which are signed in, and I take a look at them like this, and that's it. There's just two numbers and a signature on this thing. And then my colleague Chris Polly, he's at Fermilab. He also has an envelope. You don't want to trust my envelope, so we read the envelopes up. Yes, we do have the same numbers. Everyone agrees. Then you put them into a spreadsheet, and bam, you get the result like that. Instant. It's the first time we see it. We don't have any way to change it, do it, nothing. We just do it dramatically like that, and people go, woo-hoo-hoo! There could have been tears. You know, it was somewhere between woo-hoo-hoo and tears, right? And this was more woo-hoo-hoo. Yeah, anyway. And then, in all fairness, we are credible. We published on the very day we announced this 4 papers totaling more than 100 pages in technical journals, which have had thousands of citations in 2 years. So we just blew it out and did it so that every paper described in detail how the wobble frequency was measured, how the magnet was measured, and how some crazy things called beam dynamics, and then the PhysRev letter, which is announcing to the world the details. So now what? Now I get to talk to you for 5 minutes, and then we're done, about what I call the aftermath, the near term, and the far future, and lessons learned. So first, it's kind of neat. All of this hoopla is because we basically all we reported is 6% of the data that we have. So this is just a taste. It's like walking in, to the ice cream place and getting that little thing of salted caramel and saying, you want more or you don't. In about 2 months, maybe from now or so, all of this data will be released. We're going crazy on this. We're in relative stages of unblinding, multiple stages of this at this point. And all of this is just still on tape, and we're right here still collecting data, mostly systematic error data right now. But we've got, remarkably, this doesn't usually happen, we have more data than what we put in the proposal that we wanted. And we will get the result. So now, that's not going to stop people from saying and speculating what we saw. And therefore, the reason we have a lot of citations to this is there's a lot of theorists out there that go, of course you got that difference. It's because of supersymmetry, or it's because of the 2 Higgs doublet model. And here's a model with leptoquarks, and here's one with axion-like particles. So there's a lot of ways that you can add something to the model to make this work. But the little things in blue that are right there, it turns out it's getting trickier and trickier. The big colliders haven't exactly shown other hints of this stuff. That's why I gave you the lonely crack in the standard model. It feels like we're out there a little bit naked with this result, and it hasn't been supported by anything else a little bit, but these models are kind of still interesting. So then what about another thing? Now, if you're all happy right now, I'm going to make you sad for the next 2 slides. So just dumb it down to sadness now. Okay. So of course there's the naysayers in life, right? So some people, small number, but still, one group, one person, says maybe the standard model is wrong. Maybe that calculation is wrong. And so there's another way to go about this green thing here. Let me remind. This was the standard model of the theorist. This was our experiment. And now I've drawn some gray blob in between the two called BMW. And that's not the car. Believe me, I have a car like that, and they work. This is basically a model in which you can calculate it entirely on a supercomputer, this number, this one particular thing. And remember I said way back when I was showing you the kitchen sink diagrams that there's one with the little blob here? It's this little blob here which you kind of can't calculate using Feynman's little tricks. You have to do something to measure that. And that's measured by dozens of experiments. So what goes into the green band here is many, many experimental measurements of something here, in which with a very simple crank, so not tricky, gives you the green number over here. And these guys do it all with a computer. And they haven't been backed up yet, but hey, it's interesting, and as computing power is getting better and better and better, they could actually do this thing. And so we're all on pins and needles watching that. But then there's another thing. If that was bad enough, I'm going to show you something worse. And this happened just about 2 months ago, at the time when your talk is almost finished to give to a public audience. And so all of those, back here again, all of these are experiments. These are all measuring something. It's all down here that matters the most. It doesn't matter what this is so much. It's a something they measure, and they have to measure it real darn well. So there's another group in Novosibirsk, Russia, that's measuring this, basically this yellow thing here. And they finally, after some years and years of doing this with their technique, they've announced their contribution. This is just one of 6 people who've done this, but there's just one more. And where did they get? They unblinded it, and we're like, what? We were like, this is where they are. Everyone else is over here. So we just spent 3 hours, Monday morning from 6 a.m. to 9 a.m., we were listening to the Novosibirsk people tell us why they had that and defending it, and they were just as bewildered as possible because they also did the experiment before and they also got it over here, so they disagreed with themselves. But these are all measurements you don't know. They come out where they come out. So we're in the middle of an era of confusion right now, which I find a little bit interesting if you go back to the Einstein story and go, you know, there was a 1, there was a 2, and there was an up and down, and even after the 2, there were people that were getting 1 again, and like, it's in that historical, like, where are we? Real quick recap, this is the collaboration again, and this is the many institutions, and this is the evolution of G-2 experiments in terms of just pictorially these wiggles. But I want to come to some perspectives and lessons learned as I close out right now. And thank you for this wonderful photograph to UW for this. It scared the heck out of most of my friends. You know, Peter said no one would sit in the first 10 rows, which I found remarkably captured the moment. So what have we learned? What have I learned? Even trained experimenters and brilliant theorists like Einstein succumb to bias, right? Especially when the theory, like we saw, is so beautifully elegant. That's why we do everything blind. We cannot allow ourselves to be tempted to want to know the number. We've done all of our measurements blind for 30 years. Secondly, there's really these aha moments you think about in science, like, whoa, that doesn't actually happen very often. It's typically a painfully long time to discover something new. You imagine it can be decades to figure out what the heck did you see. And then in our case, we keep doubling back and saying the only thing an experiment like ours can do is control the quality of our work. That's why we have, for example, today, 6 completely independent analyses of this wiggle thing alone, and multiple of everything else, all blinded, all being checked blind with each other. That's all you can do is check every single thing. We cannot control what happens to the theory. And then I like to think, if this story started in 1908, and maybe it's going to be 5 or 10 or 20 years from now before we can sit around and say what we saw. I'm in a rocking chair somewhere, hopefully still finding out what happened. And you say, you know, what will they be saying about this work? What story will be told about this measurement in the future? Did we get it wrong? Was there new physics? Did we miss something significant? And so on. And what have we learned from history? And I want to leave you with, as we start the questions, a little thing. I asked ChatGPT to write a little poem about muons for us, and I want to thank you very much for your attention.
Thank you very much, Professor Herzog, for sharing your profound insights and, this evening, and for what for me was a very entertaining talk. My name is Jason Detweiler. I'm an associate professor of physics here at UW. And Dave, I don't know if I ever told you, but your presence here at UW was actually a major draw for me when I was applying here as faculty a dozen years ago. And I've deeply appreciated having the opportunity to work alongside you and discussing everything from strategies for career building to the relationship between the spins of muons and black holes. And, your advice and counsel, as well as your inspired leadership of our research lab, have been invaluable to me, both professionally and personally. So thank you. Yeah. So I will now be moderating the question and answer portion of this evening. And we've already received some questions from the audience. And for those of you watching online, and as well as for those of you in the room with us, we invite you to send additional questions to the email address questions@uw.edu. Or you can text your questions to area code 206-616-8160. And we will do our best to get to all of you. And I think the email address and the text number will show up here if you didn't get that.
Okay.
So one more time, questions@uw.edu. That one's easy to remember.
You want to override that? Go ahead.
Or 206-616-8160. You can text there. So, okay. So first question is a bit of like, why did you make it so hard on yourself? It looks like. So the muon, it seems like a hard particle to work with. It decays in like a few microseconds. So you have to do all your manipulations and measurements before it decays and it's gone, and that's very short time. And a muon is just a heavy electron, so why not just work with the electron instead?
Right. And this is a very common question. The electron and the muon are very similar. You can measure the electron's magnetic moment, in fact, thousands of times better than we can do it. And there's a really interesting UW history here. Hans Dehmelt put together, Nobel laureate in our physics department some time ago, he put together the techniques and really did this first. He was one of the first people to measure the electron magnetic moment at a very high level. And his postdoc, Jerry Gabriels, at the time, took this kind of idea eventually, and he was a full professor at Harvard, and just took it to another level again. And now Jerry's at Northwestern, and just 2 months ago, they've measured this thing extremely well. So it looks like they've beaten us hands down. But you remember the little funny diagram that I made with the blob, the funny blob called "This is why we have the logo, yellow and G-2"? It turns out this is where, like, the muon being 200 times heavier is basically 43,000 times more sensitive to all of the new physics because of that. And so we're always able to see things way, way better than you can do with the electron. The electron's great. It's a beautiful measurement, and it's one of the most precisely measured, if not the most precisely measured quantity in physics. It's a gorgeous measurement. But it doesn't test the standard model yet like we do.
Okay, thank you. Next question is, can you say a few more words about those agonizing months when you were completing the analysis for your first results without being able to peek at the answer in advance, and then what it felt like to then open the box and find a result that was consistent with your previous experiment and still inconsistent with theory?
Of the 200 people roughly in the experiment at the time of this, I'm guessing it was about 10 of us who had the history in the previous experiment. At the very beginning, we were guiding what was going on. Pretty soon, really smart young people and everyone new came in, and we were outnumbered 190, to 10. But we were shaking in our boots in particular because from the new collaboration's point of view, it was going to be where it was going to be, the number. And from the 10 of us or so that were on the old one, it better agree with what we did before, or we're going to look like fools. So I think you're waiting in that moment. Your heart is pounding after work. Literally, we started this in 2009 as 2021, and I was the coordinator of the analysis, no less, of this thing, so I was feeling even more pressure. And then, then I was in part of the other one, and then finally, when this is revealed, we did shriek. We did shriek with joy because, not because it wasn't agreeing with, I don't care if it agrees with the standard model, that's fine. Just that I wasn't wrong 20 years ago. Nature is what it is. All we want to do is get it right.
Yeah. Okay, the next question is a little open-ended.
Okay.
What is the importance of muons?
That is open-ended. Tim Gorge and I wrote this nice review article, I think, on precision muon physics. And the opening had some beautiful words that we scripted, but I think it's Tim mostly on this particular part. But the muon is a very interesting probe. It's used in atomic physics. It's used in this kind of particle physics. It's used in condensed matter physics as this little spinning magnet. There's a whole field called MUSR, just like where you could bring it in and it spins the materials and you get the substructure of condensed matter materials. They use the same beams. It's kind of a remarkable particle. The lifetime of the muon, this is a measurement I did also, one of mine. If you just measure how long it lives really carefully, and I did that to a part in a million precision, it tells you exactly the strength of the weak interaction, one of the four forces. So it has this marvelous way. It doesn't interact as a strong force. It's very nice like that. It penetrates through things. It lives long enough that we can make beams out of it, even though it's 2.2 microseconds thanks to Einstein, relativity. The muons in my experiment live 64 microseconds. We boost them up with relativity to that speed. So you can do that. It's a kind of an interesting particle. It decays. Because it decays by this weak interaction, it tells you all kinds of things about the structure of the weak interaction by looking at the patterns in which it decays. And so that's sort of all in the physics-y side, I'd say, except for the materials one like that. You could flip the question around and say, what good are you guys? What on earth did Why is the government spending money on you guys like that? And then you realize, look at the technologies that we have developed with superconducting magnets, with high vacuum systems, with high voltage kicking things, the fastest detectors, the fastest computers in the world. There are spin-offs. If you basically go into a positron emission tomography PET scanner like that, and they're looking at these detectors, we're doing the same detectors in my lab right now that they're trying to build into these devices. So all of that kind of stuff spins off, and probably the best spin-off we have is our human trained capital, our workforce that we have trained. Our students, our postdocs are out doing remarkable things in the world, and it's just fun to look back at that and think that all of that was kind of generated around something like this.
Very nice. Okay, for our last question of the evening, how did you get your start in this research? Say I'm an undergraduate student getting interested in getting involved in a big experiment like this. How would I get started, and what advice would you have for me?
Well, the undergraduates often do write us emails, and if they catch us on the right day, it's a funny thing like that, I hate to say it, but if you catch us on the right day, when my group just a couple days ago said, you know, now we're ready to check all these detectors out, we should really get an undergraduate in the lab to help us. That morning I had an email from an undergraduate interested with a really great blah, 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 and I thought, we got one, you know. I'm sorry it's embarrassing like that. But this is a big school. I went to a small liberal arts school, okay? There were 3 physics professors, there was no research. I had no idea physics was actually a modern science. I thought it was a historical subject, you know, went to a place like that. And I was lucky enough to go to one of these exchange programs for a quarter, a semester, or something like somewhere else. Well, not a very fancy place, but they didn't know what to do with me for my internship, and they stuck me at another university again. They stuck me in the double basement of a nuclear physics lab where I had to do stuff. And I went, people do this stuff? You know? And I was doing that, and then I just went to graduate school still kind of like, this is just fun, because it's just fun. And that's the way back. How I got into muons is a little bit of a different thing later, but it's all the same. I did lots of different experiments before muons. I did lots of things that were sort of in the genre of this, which I truly think is great to expand. Do this, do really great at that. Now, I worked with antiprotons for a long, long time. And then I just switched. Yep.
Okay. Well, thank you again, David, for your profound insights this evening, and thank you everyone who joined us in the room and watching online. And this concludes this year's University Faculty Lecture, and thank you and good night.
Thank you.